Thank you, Lena, for the introduction, and sorry for the bit delayed beginning. So, welcome to this vendor session on Dynawo, an hybrid C++ Modelica open source suite of simulation tools for power system simulations. So, my name is Adrien Guéronnet, and I'm project manager for power system simulation tools development in RTE, which is the French transmission system operator. So this vendor session will be certainly a bit different from the other ones because for two main reasons. The first one is that we won't talk about a completely generic Modelica tool, but instead of a domain-specific tool, which is basically a tool that has been developed for power system simulation or energy system simulation in a more broader way. The second difference is that I won't really demonstrate the tool usage with nice GUI and all these features, because we will talk only about the core part, the simulation tool, which doesn't encompass a GUI, data management, and so on. So it's a tool that has to be included into a simulation environment. We are just talking about the simulation tool here. Anyway, I hope that even if it's a bit different, you will learn some things through this vendor session, and that you will get interested in the topic and in the approach we have developed in this tool. So the outline of my presentation will be quite simple, with first a few reminders on what is power system simulation, what is the traditional way of doing tools in this domain field, and so what we propose here and why we turn to Modelica. Then an overview of the tool itself, what we plan to do in the future, and what are the perspectives, and a few examples of usages we already have here in RT or with partners. And I will end with of course, conclusions. So maybe just to remind everyone what we're talking about. We're talking about power system, and in particular, power system simulation that should be conducted by power system operators. What is a power system operator? And in this particular case, even a transmission system operator, it is an entity, company that operate independently from the other electricity market players, and that must make sure that the transmission or distribution of electric power is working fine. It means there shouldn't be any discriminatory or we should ensure transparent access to the grid. The grid should be self-operated, self-maintained, and we should also take care of the development of the grid in the long term. Just to give you also a few figures to illustrate this, in our case, RT is a French transmission system operator. It's just an example, but it's a bit of representative of what we're talking about. RT is in charge of quite large infrastructure, more than 100,000 kilometers of line, and with a peak load served that is higher than 100 gigawatts. More than 2,000 also substation, quite a large infrastructure. And so why we do simulation in this context, we do simulations in order to ensure stable and secure operation means. It means that at any moment there should be an acceptable steady state for the system, and it should be also a stable system. We should be able to go from one operating point to another without any problem. So in this context, we conduct power system actors, transmission system operators, but also others, producers, distribution system operators, vendors, manufacturers, conduct a lot of simulations for different needs. So in our case, it's more static dynamic security assessment, being sure that the system is in an acceptable state, and we do it for different time scales, for short-term stability, long-term stability, from a few microseconds to a few minutes. And we do it also for operational context and planning studies, which is which new things should be added into the network. And of course, it's generally speaking simulation in which you have a large number or large range of phenomena to investigate, and they have different time constants. So you have different kind of final application tools depending on what you want to search for and what you want to guarantee in terms of stability. What is also important to keep in mind regarding the power system is that it is a system that is under a dramatic evolution path, which dramatic in the sense an important one, not it's not dramatic because we are going towards certainly a better system with more renewable energies, a cleaner system. But it means that the system is changing a lot. It's if we try to sum up this in one sentence, it's basically in the past we have a system that was quite easy to predict, with mainly driven by large synchronous generator units, nuclear power plants, fuel power plants, hydro power plants, and we are going towards something that is more complex, more unpredictable, and also more numerically driven, a turn towards more cyber physical systems with more renewable energies, more controllers, DC networks, power electronic-based components. And all of this, of course, makes it more difficult to be sure to operate the system in a stable and secure way. So in order to do this, we need, on the simulation side, to be able to collaborate in a better way, to have more transparent tools and to have more flexible tools, because the world is changing and it's changing in a faster way. So if we keep this in mind, and now we go towards what is generally speaking available in power system simulation tools, we have mainly closed and proprietary power system simulation tools with their own data, with their own format, with their own solvers. So it's difficult to really get deep into the explanation of the results. It's also difficult to introduce new components or to question the existing approximations. On top of that, another also existing drawback is that these classical tools have been developed for more than 20 to 25 years. And so they contain very strong hypotheses on the power system structures, such as, for example, the existence of a synchronous generator machine, which could no longer be the case, at least temporarily, in the future systems, where we could have situations in which we only have, for example, renewable energy sources feeding the consumption. If we look to our needs and the changes that are going on and the tools that we have, it doesn't match. It doesn't match, and we can't really go on with such an approach because it clearly limits the possibilities in terms of collaboration. The transparency is not guaranteed because you don't have access to the final code, and you don't even have access to the implementation of the models, for example. And the flexibility is also limited because you have very strong hypotheses into the tool. So it leads us to what was the motivation and what we did the Dynawo initiative. So what is the Dynawo initiative? It's a complete change in terms of the way to do power system simulation tools. Of course, for you, it won't be a change. I mean, for people used to a Modelica approach or to use either Dynawo, Modelica, or another tool, it won't be a change. But for power system actors, it's a complete change. The idea was to say, let's just stop doing the traditional tools and let's try to really do this transparent thing, this flexibility thing, and ease collaboration. So going to transparent open source, going to the use of a high-level modeling language, and keeping a strict separation between modeling and solving parts to ensure flexibility and possible improvements. Well, so this switch, it has been forced or pushed by several people, but also in particular by RT, not only RT, but also RT and several other people in the power system community. And the idea was to say, let's now try to develop this new approach with partners, and in order to set up something that could be easily reusable by every interested power system stakeholder. So that's basically the basis of the Dynawo initiative. It begins with the first phase, if I can say, conducted through two main European projects, which are right now 10 years and 5 years ago, 5 years old, but that was PGAS and iTesla. Both projects try to use Modelica for power system modeling and see, well, is it doable or not? Of course, there were already some usage of Modelica for power system or for energy system simulations. That were not the first one, but that was certainly the first project in which the power system community was very active and proactive. Of course, no, we are surprised at the end. We can do power system simulations with Modelica, no problem with the language. I can write the equations I need. I mean, power system is complex, but it's certainly less complex than other application domains of Modelica. So it proves that I can reproduce existing results. But there were a few limitations in this project. The first one is that full Modelica tools are not compatible with an operational use at the moment for performance reasons, and also in the way the models were developed. They were developed in a very similar way than in previous traditional tools, and so the readability and the transparency, even if it's open source and in the Modelica language, were not really so much improved. And so, well, what we do here now in Dynawo, and what we try to manage to do is developing on this basis, developing a complete source of simulation tools, a complete suite of simulation tools, hybrid C++ Modelica, while keeping two core principles in the tools. The first one is trying to use as much as possible Modelica and just keeping C++ for a few components. I will give you a bit more details later on, and also keeping the strict separation between modeling and solving parts. So the idea is still to ensure flexibility, transparency, and quality. And maybe the difference, because it could be a natural question, what is the difference with more established Modelica tools? The difference is that we also provide a few features that enable to really speed up the simulation time and come back to performances that are close to current traditional tools used in power system simulations. So it's trying to keep the advantages of Modelica tools and bypass a bit of the performance issues with an assumed strategy related to compilation. I will explain this later on. So if we right now go a bit more into the details and have an overview of the tool and its functionalities, it's quite the same slide than previously, just to with a bit more details on the figures. The idea is to say, to give you a bit of knowledge of the architecture, basically. So we have models and solvers separate. On the solver side, we try to use as much as possible open source solutions, and open source solution developed by applied mathematician teams in order to use what is the best for our kind of problems. And in the modeling side, we can use either Modelica and C++, and they are kind of handled in a similar way to give a unique common interface to the solver side, keeping this strict separation between both parts. Again, with the tool also comes a library. It's not such an open tool or generic tool, as I said in the introduction. The idea is to do power system simulation or energy simulations, and so we provide with the tool also library. So the idea is here to give you a bit more insight into this library. So the Modelica library is, of course, the library is still under development. I mean, it's a living project, but the Modelica library has grown quite a lot in the last few months and years, and so we know which quite a first satisfactory number of models. So this library also, what is important is that we try to design it to, of course, take advantage of the declarative modeling approach. So it's no longer the same idea than, for example, in IPSL. The idea is not to write the models in a similar way than in traditional tools. It's really to use a declarative-based approach and keeping equations as close as textbook equations in case of physical modelings, and in case of block controls, trying also to do blocks that make sense, and to use the flexibility of Modelica to simplify sometimes a bit complicating existing structure. It has also been organized in a way to have access to basic blocks and avoid duplications and redevelopment of existing code. It means you already have access to a few blocks that you can combine to create your own final block, or at least to build upon to create your own final block. So in terms of content, where we have classical network components, I can show you later on in OMEdit. We also have more advanced models for HVDC, static vector compensator, also standard models for normalization organism for renewable energy sources, and a lot of control and special protection scheme models. In addition to this Modelica library, we still have a few C++ models to cope with two main topics. The first one is being able to connect and disconnect dynamically components during the simulation, which means we have dynamic connectors. So that is done in C++ at the moment, and also for wide area controllers such as the frequency regulation, where you can have a very different number of components connected to the controller depending on the simulation you do and the area you consider. So I will just try to go to show you now the library in Open Modelica. Maybe let me just a few seconds so this is not share. I will just stop share and share again to. Oh yeah, here it is. Here it is. Let me just show you the structure in OMEdit. So you should normally speaking right now see my OMEdit screen. So you have, as I said, the Dynawo library, which is organized in a quite classical way. You have users guide examples. We also put as much as possible full Modelica test cases. The idea is to say Dynawo is not like is not against existing Modelica tools. It's complementary. So if the performance problem with existing Modelica tools get away in the future, then we will perfectly switch towards using generic Modelica tool. And already for small test case or small to middle-sized test cases, we can use Modelica tools. And so there are examples based on the Dynawo libraries that simulates just in Modelica tools. Then you have the electrical models. So you have most classical electrical models. So you can see buses, lines, transformers, and so on. So if we go to the machine one, for example, and we open a generator synchronous model, you see that we have, oh, this is not the one I wanted to see. Sorry, the equations are there in addition. So you see we really have equations for people that know synchronous generator synchronous model. It's quite close to what you would find in the Kundo book, for example. And you don't have any causality defined. You have parts equations that are separated in different parts corresponding to either a part of the physical model. Yeah, you also have, of course, a control part where you have all the control things like, for example, if we look to grid forming things or things like this, in this case, of course, you are more in a block scheme approach. And what we have done, as always, is also having base controls such as the current loop, the voltage loop, and then you can reuse them to create your final grid forming controller, which we use at each time a current loop, a voltage loop, a DC voltage loop, and then they just the final one block that differs from one model to another. So again, that's the same idea. For example, on the HVDC, you have different elementary controls that you combine together. For example, the DC line, you can reuse it in another HVDC model. And then in addition to this, you also have, like, of course, non-electrical components and additional blocks that we have defined that are a bit specific to the library under our use, and that doesn't exist in the Modelica standard library. Otherwise, the idea is to use as much as possible the Modelica standard library. Connectors, tips, and additional examples. So that was just a quick overview on this. I will just come back to the presentation right now. Yeah. Okay. Yeah, so that was for the model part. If we go ahead right now, the counterpart is the solver side. So at the moment, there are two solvers included, a backwater server, mainly for long-term stability simulations, while that's also inherited from the Pegasus Open project. And we use also efficient numerical methods for sparse problems. Power system problems are by definition very sparse because each bus is, for example, only connected to a few buses and not to the whole graph. So we use both Kinser, KLU, and KSLU for the LU decompositions. And we also have another server, which is inherited from the Sanders efforts conducted by the Lawrence Livermore National Lab. It's a variable time step variable order method, which is IDA, that has also been included in Open Modelica, for example, and it's a BDF variable order scheme with root finding method to detect the exact moment of event. With such a method, you also have an accuracy that is guaranteed by the use of a local truncation error scheme. Well, basically, so at the moment we have two solvers, one which is more when you do long-term stability problems, when you want not to have a guaranteed accuracy, but indeed to speed up a bit the calculation. It's the first one, and the second one is really for accurate simulations. As you can see on the plot, that's the same models, the same simulation, but with the three solvers. With the two solvers, and IDA could be either used with a maximum order of 1 or 2 in the BDF numerical scheme. And you can see that, of course, the backwater implementation smooths the oscillation, whereas when you go to a variable time step, you get more details. Let's now come back to what I introduced as key features we want to provide: flexibility, performances, and robustness and accuracy. In terms of flexibility, or we provide flexibility, I already showed it a bit with the libraries. Of course, it's quite easy to introduce new components just because we use Modelica, but also because we have common blocks, we have an architecture, we have a coding style, and so on, and more examples to build upon. It's also quite easy to modify existing components because we use this kind of block combination approach. So if you just want to change the physical parts, you just replace the physical part. If you just want to change a PLL, you just change the PLL and so on. What is also important to say is that, of course, we provide a library with the tool. It's a Dynawo library, but it's also possible to enrich this with your own models or with other libraries that has been successfully done with, for example, the electromagnetic transient Modelica library developed by the École Polytechnique de Montréal. And there will be a presentation on this library this afternoon if you're interested also. And also with few models of the power grids library that we have developed together with Francesco Casella and Dynamica team. Of course, you also have still the strict separation between modeling and solving side, which means that you can develop new solver without knowing so much the models. And you can add a new model without having to do anything on the solver side. Well, I think you all have this in mind, being able to Modelica tools, but again, for more power system people, generally speaking, changing the solver is something that is not doable in existing tools. In terms of performances, well, the key thing here is that we do something a bit special in Dynawo, which is to precompile and generate models library at the compilation time, and we only instantiate the models at runtime. This is particularly efficient in the case of power system, where we have only a few number of models, but we instantiate them a large number of times during the simulation. And this is done through a customized pipeline on the Open Modelica compiler. Basically, what we do is that if you take a power system model, such as a generator, basically it's a rectangular model because you miss equation. But you know very well the interface. You know that it will be connected to the network, and so you know that you missed basically the voltage. We with the Modelica model and an additional file describing the missing equations or the missing variables, we build automatically a square model that we compile with Open Modelica. It gives us a square C++ model, and then we just remove the fictitious equations and end up with a model that is identical to the original one and that we can only instantiate at runtime. It means that in our case, compared to generic Modelica tools, we don't have compilation at runtime. We just have simulation, and in our case, where we go up to a few hundred of thousands variables in some cases, it saves a very large amount of time. In addition to this, we also have done a certain number of software optimization in the core part itself. Of course, based on some ideas already existing in Modelica tools, aliasing, also observers mechanism, and also automatic categorization of the variables in order to save useless treatments during the simulation times. If we go to accuracy and robustness, of course, you have detailed modeling, you have a solver with guaranteed precision, so you can go to very accurate simulations, and then you can use them as a reference to do an approximation-driven approach to validate, certify your approximation compared to the most detailed simulation, and while staying in the same environment. So robustness is quite natively provided by building upon existing tools and existing well-robust tools or language, Modelica and Modelica standard library, Open Modelica, and something else for the solver side. And the robustness has been successfully proved during some parallel run conducted in RT with more than like 100 thousands of simulation conducted without any problem for voltage stability assessment. This approach, this tool, is also an industrial grade framework because you also have access to additional functionalities, additional compressive set of outputs. You have access to timeline, curves, the disconnected components. You have access to the final state, and you of course have access to a logging system and to the result of the initialization if you want to understand what's going on there. You also have the possibility to stop the simulation if based on some criteria. For example, if the voltage is lower than a certain value, you can just say it's unacceptable for me. In addition to this, in addition to the unitary simulation aspects, you also have ancillary services to launch like multiple simulations that are very common usage in the power system community, such as the contingency analysis, where you will just disconnect one by one all the components and see what is the effects, also margin calculation or validation tool, being able to launch several times the simulation and compare the results if you change this parameter or this model. And it's also a framework that is industrial because it's also industrially used. It will be, it's not the case right now, but it should be in a few weeks. From November, it will be used operationally in RT control centers to assess voltage stability on the French national grid, and also to study the interaction between the special protection schemes. As I said also in the introduction, it's not a complete environment, it's just a simulation tool. Nevertheless, there are clear and well-defined APIs, so you just need a few input files to launch the simulations, and then it's quite easy to integrate the tool into simulation environments. We have done this in RT with our traditional simulation environment, Convergence, but we also do this with the Linux Foundation Energy project, Possible, that enables to launch Dynawo calculation. So, so it's a simulation tool, but with the clear APIs integrated it into existing simulation environment is quite doable. Of course, it's also working on different operating systems, Linux, Windows, and we also provide, in addition to the source code, distribution versions and some Docker images that could be either pre-built if you want just to use them as a user, or more developer ones. Indeed, so I talked a lot about a frame, and this frame can then be declined into different application tools, and that's what we currently do. We have several tools that do a different trade-off between accuracy, performance, and flexibility, depending on what you want to study and the phenomena you want to investigate. So it's the same kind of approach, and I will illustrate this on my next slide, but the choice of models, the choice of solvers differ. So you have a tool for more steady-state calculations, you have a tool for short-circuit calculation, you have a declination for voltage stability assessment, transient stability assessment, or simulation with a large number of P-based components. In terms of architecture, what I said is that basically lots of the tool code is similar. You have common high-level objects, APIs, one compiler, some models that are commands, and then you just specify a few models and the solving strategy to either orientate your final application towards more accuracy or more performance, depending on the phenomena you want to catch. Yeah, let's now switch towards roadmap and perspectives. Of course, we still work on the model development and the Modelica library, so that could be used in Dynawo or in other tools with additional components in the same time frame for existing usages, asynchronous generator model and conventional load models, more regulation models, standard IEEE, IEC regulation models, and additional special protection schemes. But also new usage like three-phase classical models. Most of our models right now are one-phase, and some advanced controller models with dealing with imbalances and so on. And also what we want to push with the frame and with the use of Modelica is also for like standardized model, also refining, questioning them, and doing variants that will be available for everyone and that enable to highlight some potential drawbacks of the current norm or possible needed additional things to put into the norm. So that's the first axis. Of course, we still also work on the solvers development. So on two aspects, basically. The first one is adding classical traditional numerical schemes, quite generic one, like we are currently doing a trapezoidal method development that is widely used, for example, for electromagnetic simulations in the power system community, but which is a well-known massive numerical scheme that is also used in other contexts. But also trying to develop with both power system and applied mathematician partners more specific numerical methods that would be very efficient for power system simulations and specific power system simulation. The first one is, for example, I just provide two examples. The first one is the sinusoidal predictor method that we developed on top of the AIDA variable time step order. It's a method that enables, in case of oscillating variables, to increase your time step to a value that is higher than the frequency of the oscillation by decomposing your problem in a part that is oscillating at a certain frequency and the rest of the signal. We also have, it's hidden by the figures, but we also have currently a collaboration to better handle asynchronous digital controllers with variable time step solvers. So it's, well, power system is definitely a specific use cases for this kind of thing, but the reflection and the thinking is more general than just power system. In terms of performances, also several works either under progress or that just start. One nice collaboration that just that will start with Open Modelica to have access to the analytical or symbolic Jacobian in Modelica, in Open Modelica for the E mode. Of course, otherwise evaluating the Jacobian should be done through an automatic differentiation approach, and it's quite costly in terms of simulation time. So it's a bottleneck for us for pushing for more Modelica-based simulation. So having this available in the Open Modelica compiler will make it possible for us to use it in Dynawo and to speed up both Open Modelica and Dynawo simulation. And in addition, we will also still try to decrease further the number of variables and to better characterize the event type and the characteristics that impact on the system. And the last direction in which we work also is still offering more features in the tool, more ancillary services, critical clearing time calculation algorithm, which is in case of short circuit calculation, the automatically detecting, calculating the maximum length or time duration of the short circuit between losing synchronism, which is an interesting feature for system operators. Also, a coupling, for example, the simulation tool with real-time algorithm used for model analysis to provide a different approach in terms of model analysis than linearization, where a lot of questions are open on the way you linearize, for example, saturations and so on. And also introducing Dynawo into an automatic toolbox for model validation, where you will compare the simulation results with measurements that you can have on fields, and so trying to identify the parameters that is not accurate enough. We also work on the robustness to try to support a larger range of the Modelica language, and also to be able to disconnect the system in different parts during the simulation. And the last but not least point is also to ease the transition between generic Modelica tools, Open Modelica, Simula, and Dynawo. So the two main questions here are the question of initialization, and should we find a way to align the methods used, and also trying to simplify the way we build final models in Dynawo, so that people can switch from Open Modelica, Dynawo, and use Modelica to Dynawo in an easy way. Well, I will end up with a few use cases to just show you what you can do with the tool. Quickly, a few words on the test cases. So we already provide with the tool test cases like single machine infinite-based system, Kundu, four-based test system, some IEEE test cases, 1457. So more under review or development, IEEE 9, IEEE 118, which leads us to middle size test cases, and so you control a test network, which is a classical test network for transient stability analysis. And we plan to add also more classical ones for voltage stability analysis, and also providing large-scale French test cases to help researchers having access to real data. The only point is that we need to end up the anonymization process. Well, I will give you illustration of the different possible use case. So the first one is steady state calculation. So in this case, we do simplified time domain simulation to find the correct final steady state, especially when there are several controllers that interact. So this extracted from paper we published at the last PowerTech conference, but it's a very simple but illustrative test case. You have a small network and you have phase shifter, which are special protection schemes that change the current in a line, but that they have a temporized action. So you change the current every X seconds. And so depending on the interaction between the two protection schemes, you will end up with different final states. And that's something that couldn't be seen by classical power flow simulation tool. So this is something we can do easily with our approach. And we end up with simulation times that are close to current simulation time, like 3 seconds in our case on a French test case for this kind of simulation against 1 second in traditional test case. Another use is voltage stability assessment. This here represented for the IEEE 14 test case, which is available in the example section of the tool. So you study the disconnection of a generator 2, that will lead to the disconnection of another generator 3. And what you can see, even if it's not very clear, is that here you have on the left part, you have the type change actions that try to restore the voltage. And you can see the voltage decreases, and then the reaction of the voltage control of the generators remaining in the network enable to stabilize the situation. Also, a more industrial example, it's a voltage stability assessment on the French network. So you can see that we see the voltage collapse on the top left part of the slide, where the purple and yellow voltage decreases a lot. You can also see the comparison between the new tool, Dynawo, and the previously used in RT. So you see the voltage collapse behavior is quite similar. It's quite driven by the same mechanism. What is important to notice that using the new tool with more detailed models and being able to combine different level of modeling details, we managed to increase a bit the operational margin, which is quite nice. And in terms of simulation time ratio, we get very close to the existing tool. So it means that we managed to bypass the performance barrier. Transient stability simulation could also be used with a tool. Again, it's in the example section. It's an example extracted from Kundou book Power System Stability, which is the offense book for power system stability. And you can see the results you obtain when you simulate this test case with a generator without any voltage regulation scheme, with a voltage regulation scheme without power system stabilizer, and with power system stabilizer. And we managed to obtain exactly the same results than in the original textbook. And it's also to say that, of course, we're talking about an industrial tool, the industrial approach, but the library itself and the tool, if you want, could also be used for educational purposes or teaching purposes. And Modelica in this direction in power system is also a good idea. And the final illustrative use case is doing validation. So we currently also develop and will release open source soon some automatic workflow to compare outputs from different tools, and also to compare results, launch and compare results automatically between different implementation or instantiation of the Dynawo tool itself. So it could be quite interesting if you want to study the impact of, for example, the numerical scheme on the results you obtain, or to see the impact of a certain change in a parameter in a model, or or changing a model. For example, if you go from a very detailed model to a simplified one, then you can launch a batch of simulations, and we have a Jupyter Notebook approach to show you the differences and so on. Well, it leads me to the conclusion, quite in time. So the Dynawo tool is an hybrid, is indeed more an approach. It's an hybrid C++ Modelica open source suite of simulation tools. So basically, it's a framework, and then you can decline it into different application tools. It's the result of strong strategical choice from RT to push for open source solution in the power system community. I will also mention the creation of the Linux Foundation Energy at the same time, also by a few actors, including RT. So really a turn towards the open source problem or the open source question in power system. It's no mature project. I mean, it has been developed for more than 5 or 6 years at least. It's open source, so you have access to the final implementation of the model, to the final numerical scheme used, no hidden treatment, and it's also no longer just a research program. It's an industrial grade tool. It will be used operationally in RT to take decision. I mean, to operate the grid. So a reliable tool. Of course, what has been motivating us or pushing us to do the choices we have done is guaranteeing flexibility, transparency, quality, and acceptable performance. So yeah, I already mentioned that, but there are more and more people interested in the power system community for open source solution, and we already have an active group of different partners that support or contribute to the project and the framework. So if you are interested, don't hesitate either to try it, go to the website or to the GitHub repository, or to get in touch with us. So thank you for your attention, and if you have any question, please feel free.